Welcome back. This title is quite lengthy, but the title itself is like an introduction to the topic, which is the rationale behind the existence of many thermodynamic functions or thermodynamic potentials. Okay, see, these are different state functions: entropy, internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy that you see being utilized in thermodynamics. And why do they exist? Why do we come up with these different thermodynamic potential? Will be explained in this lecture in connection with the experimental conditions. So this is something which students are not very clear even after a course. So it's important that you understand this lecture well, and if there are questions, we can of course discuss in the discussion. So the previous lecture was last of many lectures on exergy. Exergy is quite important from a practical engineering standpoint because exergy refers to the work potential of a system. So exergy, the way it is defined itself is slightly abstract, so you have to really relate to it via different examples to get a better feel for what exergy is. I always say that exergy is the other side of entropy. Okay, so if you want to understand exergy well, you should also understand entropy generation very well. Okay, so exergy destroyed is close related to entropy generation. Like entropy, exergy is not a conserved quantity. Therefore, when you try to write a balance equation, you have a term which is not present in, let's say, mass conservation or energy conservation. Okay, so exergy conservation, for example, when we saw some particular processes, flow processes or exergy balance over a control volume, has this kind of a term, exergy destroyed. Okay, so I mean, this is a general balance equation, and we applied that to a control volume. So when you go to entropy balance, you will have an entropy generation term. Okay, so these two are just two sides of a related process. So we can, of course, write the exergy balance equation in terms of per unit time, in terms of rate, the rate form, and then we derive certain equations. So whenever you are trying to compute exergy or entropy, it's better to implement the strategy which makes use of the fact that exergy and entropy are state variables. Okay, so the computational procedure which you're going to adopt should take this into account. That's why the two TDS relationship were very critical for entropy balance. Okay, so we derived two TDS relationship. So instead of looking at processes, okay, so that can be quite confusing. So instead of just looking at processes, it's important to look at a computation procedure that takes into account the state function nature of entropy. Okay, so so the same thing applies to exergy also. Okay, so look at a strategy that looks at the state property of exergy and then implement that strategy for the particular system you're looking at. So why did we do all these exergy balance? It gave us something like a second law efficiency, right? So what do you mean by second law efficiency? If you imagine a process, there are the ideal case where, let's say, maximum work that can be obtained. That is done when you have a reversible nature. Okay, so of the process, and you compare that ideal case, that is a reversible nature, versus what you actually have. Okay, so that gives you a certain kind of efficiency, and this efficiency is related to exergy destroy. Okay, so which is the difference between the ideal work input, in this case the reversible work input, minus the work input you actually see in the process. As I said, both entropy generation, exergy destruction are connected. So of course the second law efficiency is connected with entropy generation. Okay, so, and we established slightly different forms of second law efficiency formula because in some cases, what is the ideal process with which you want to be comparing is not very clear. Okay, so for in this case, we have given the formula for mixing. Okay, so in some cases, the reversible process is obvious, but in some cases, it's not very clear what is the equation. So we looked at certain case studies to clarify the nature of second law efficiency, the formula that we utilize for second law efficiency. So that concluded the exergy balance. And then we are going to start a new topic in next few lectures, starting from this lecture. So if you remember, we saw an important extremum principle for an isolated system. So we derived this relationship, and we stated that if you have an isolated system, entropy of that isolated system will always increase. So at equilibrium, the system as isolated system has reached equilibrium, entropy would be a maximum. Okay, so, and we also saw related extremal principles with respect to exergy too, but entropy is, once you address entropy, exergy in a way follows. Okay, so here we would, in this lecture, we would see that such extremal principles are also available with respect to other thermodynamic potentials. Okay, so first we have to clarify where we will be using these other thermodynamic potentials. What are we talking about here? So U or E, okay, both are equivalent symbols, that is used for internal energy. And we have already seen where we utilize enthalpy for flow processes. So enthalpy was defined as U plus PV. And we are going to introduce two very important thermodynamic functions, the state functions. Helmholtz free energy, which is defined as U minus Ts, and Gibbs free energy, which is defined as U plus PV minus Ts, or equivalently, G is equal to H minus Ts. Okay. So first you can ask, why do we have 5 thermodynamic potentials? Okay, so we will also clarify this term potential at a later stage. Why do we use this term potential? Okay, it has these, okay, so, or for now, just we'll use this, we'll refer to these 5 functions as thermodynamic functions because they're all state functions. So what is the need for 5 state functions? Okay, so if you actually see why we are having 5 state functions, it is because of there are a variety of ways of doing a particular experiment. Okay, so the boundary conditions relevant to the experiments are different. Okay, so what exactly do I mean by that? So what is the controlled variable? What is kept a constant, and what is allowed to change or fluctuate, okay, is different in different experiments. Okay, so when you have an isolated system, you control the total energy, you control the total volume, you control the total number of atoms in the system, in an isolated system. That's a system that is useful for formulation. However, it is very difficult to implement an isolated system in real experiments. Okay? So most of the real experiments are conducted under two conditions. It's easy to keep the total number of molecules constant. You can close the system. You can also keep a volume constant. That's if I have, let's say, a closed beaker. Okay, so I can keep the volume constant. No molecules are allowed to escape or enter the system. And then you can also keep temperature a constant. Supposing I have a closed test tube. I have a test tube and I have closed the test tube with a cork. Okay, so the volume is fixed. That is the volume, and I have a gas mixture in the test tube. So, and this entire closed test tube is interacting with the atmosphere. So it will take the contents of the test tube will take the temperature of the atmosphere, surrounding atmosphere. So T is kept a constant, volume is a constant, and the total number of molecules is a constant. Why? Because I have closed the test tube. In some other case, I can also do an experiment where the pressure is kept a constant, temperature is kept a constant. Let's say I have a liquid mixture. Okay, so in this case, there is a liquid which has the same pressure as the atmospheric pressure and the atmospheric temperature. Because it's a liquid and the liquid is not evaporating and so on, the total number of molecules is also a constant. So there are a variety of ways of doing the particular experiment. So you can, so depending upon the experiment you are doing, you would see that different thermodynamic state functions, these 5 different thermodynamic state functions, will take an extremal value. That is, it will either be a maxima or a minima. Only entropy takes a maxima, and all the other thermodynamic functions discussed here, internal energy, Helmholtz free energy, enthalpy, and Gibbs free energy, will take a minima. So we will just prove that, we state that it takes an extremal value. Why it takes a maxima or a minima, we're not going to prove here. It can also be proved, okay, depending upon certain stability condition. But for now, we're just going to state that it takes an extremal value, and which of these 5 variables take a maxima and which will take a minimum. So what is the take-home message here? Depending upon the way you do an experiment, the experiment is defined by the boundary conditions. That means what is kept a constant. And depending on the experiment, one of this thermodynamic variable is utilized more than the other thermodynamic variables, thermodynamic functions, because that particular thermodynamic function is going to take an extremal value. We'll clarify this again in the next 2 slides. I just this is the information that was presented in the previous slide. All we are going to do is we are going to differentiate, implement the first differential of these thermodynamic potentials. So this is just a restatement of the first law, right? So change in internal energy is equal to Q minus W. So here I'm not looking at electrical work, magnetic work, and so on. So this is the simplest system with which you can work for first law. So you just have PdV work and heat interaction. So the heat interaction and the work interaction can be rewritten in the following manner. We have already seen this when we discussed first law, and we have also seen this in the context of first law. How do I get this? I differentiate dH, and for du, I put this quantity for du. When I do that, I get dH as Tds plus Vdp. And then I can have a similar procedure for computing dA, that is first differential changes in free energy to the first order, and dG changes in Gibbs free energy to the first order. How did I get dA? Because dA is U minus Ts, A is U minus Ts. So when I have dA, I have du minus T ds minus S dt, right? So, and for du, I substitute this form. When I do that, I will get dA is equal to minus S dt minus P dv. So, likewise, I can have a form dg is equal to minus S dt plus P dv. To get dg, I substitute this formula in here. When I do dg is equal to du plus all the other terms, I substitute this formula into this, I will get this thing. So what do you see? There are different ways I can conduct the experiment. I can conduct the experiment by keeping V and T a constant and P and T a constant. That's what we discussed, right? So it's very easy to conduct these experiments in these two manners, right? Keeping V and T a constant. If I have a gas mixture, all I need to do is close the bottle. Okay, so if I do that, I can control V, I can control T. And many times in, let's say, solids, okay, so solids in material science, metallurgy and so on, if I'm looking at alloy mixing and so on, okay, so one of the most important phase diagram I said is the iron-carbon phase diagram. There you conduct the experiment at constant atmospheric pressure and constant temperature, all right? So again, I can conduct the experiment by keeping P and T a constant. Okay, so if you so you can ask, how many things have to be controlled? If you remember, the answer to this question lies in Gibbs phase rule. When we addressed phase diagram, we also addressed Gibbs phase rule, and we decided on the number of variables that can be controlled, that has to be controlled for defining the system, right? And in contrast to keeping V and T a constant, P and T a constant, controlling S and V and S and P, that is, how do I keep entropy constant? Okay, so that is not an easy experiment. Okay, so that is the difficulty in challenge in doing an experiment by keeping constant entropy. Okay, so you don't often see an experiment where entropy is kept a constant. However, constant T and V, constant P and T are more easy experiment. Supposing you keep T and V a constant, what do you see here? dt is 0 because T is held a constant, dV is 0 because V is held a constant. So for such an experiment, dA changes in Helmholtz free energy to the first degree should be 0 because dt and dV are 0. Likewise, when I have an experimental system where T is held a constant, there is no change in temperature, there is no change in pressure, dt and dP are 0, therefore Gibbs free energy to the first degree is 0. Okay, so likewise, you can have, supposing you are able to design an experiment where entropy is kept a constant and volume is kept a constant, du would be
0 for such a system. Change in internal energy to the first degree should be 0 for a system where S and V are kept a constant. And if S and P are kept a constant, so ds and dP are 0. Therefore, dH to the first degree is 0. So, in effect, what I have is different experimental condition. Okay, so what am I representing here? If I am looking at a system wherein I'm controlling total internal energy, total volume, and total number of molecules, okay, inside the system, that's an isolated system. The potential thermodynamic function or thermodynamic potential I would be interested in the sense that what is the thermodynamic property, thermodynamic function, thermodynamic potential that takes an extremal value for that experimental system? That's the question I'm asking. So entropy is the relevant function. This is a isolated system. We have already seen that. Likewise, if I am able to control entropy, volume, and N, okay, so I can keep these a constant. Internal energy is the thermodynamic property, thermodynamic state function, thermodynamic potential that gets extremized. Okay, so and so on. Okay, so all these take an extremal value. These four quantities take a minimum value. But for now, we have just argued that it will take an extremal value, but I'm also stating that it will take a minima. Okay, I've not proved that, but we can prove with simple arguments why it should take an extremal value. So you would often see that Helmholtz free energy and Gibbs free energy are often used in the thermodynamic description. Okay, so why is that? Because it's the thermodynamic function that is most relevant to the experimental condition. For solids and so on, you typically conduct the experiment at constant temperature and constant pressure, that of atmospheric temperature and atmospheric pressure. Therefore, Gibbs free energy is the thermodynamic property, thermodynamic state function of relevance. Okay, this particular thermodynamic state function, Gibbs free energy, is going to be a minima at equilibrium for such a system. What is a system? A system for which temperature, pressure, and total number of molecules is a constant, is controlled. Likewise, if you have a system, for example, a gaseous mixture, you ask, what is the condition this gaseous mixture takes when it is at equilibrium, when we control total temperature, volume, and total number of molecules corresponding to these three variables that are controlled. Helmholtz free energy is the relevant variable. Helmholtz free energy takes an extremal value, that is, it is a minima at equilibrium for such a system. So again, to re-emphasize what I stated in the previous slide, depending upon the different experimental condition, I choose what is the thermodynamic property that takes an extremal value. Therefore, I utilize that. I call that as the natural thermodynamic function for describing the system. G is the natural thermodynamic function for describing an experimental system in which these three are controlled. Helmholtz free energy is a natural thermodynamic variable, natural in the sense that takes an extremal value if these three variables are controlled. So in all these three systems, in these two systems, entropy is controlled. That's a hard experiment to do. And this isolated system is again not seen in reality. Okay, so even though you can formulate many things mathematically, you don't often see them being utilized. Okay, so in most systems, you see these two as being used. Okay, in some of the engineering flow systems, we also see enthalpy, but these are the two common thermodynamic state functions that are often used. So there is another way to get to the same conclusion. So here we are looking at the system of interest. What is the system of interest? The system of interest is like a closed test tube. Okay, so let's say you have a gaseous mixture. There can be combustion. There can be some property that is some change that is occurring in the system, but all the changes are occurring within a rigid container. This rigid container volume is fixed, therefore there can be no PDV work, and volume is fixed, and no molecules can enter or leave the system. Okay, so that this is the system of interest, but it can have heat interaction with the environment, right? So it can be just the environment is usually the atmosphere in which the system is present. And then I draw a boundary far enough from the system of interest, and I can say that this system of interest and the surrounding atmosphere is an isolated system. And in this is an isolated system, and heat is being transferred from the environment to the system. Because it's the combined system is isolated, changes in internal energy of the bath, that is the atmosphere in this case, and the changes in internal energy of the system is zero. Okay, the overall change is zero because it is internal exchange. Okay, so all right, so this change is counteracted by this change so that the total change is zero. And then from second law of thermodynamics, I know that for this combined system, entropy change has to be greater than or equal to zero. So what is the entropy change? This is the entropy change. Del S is the entropy change of the system. The system can be anything can be happening in the system, but the system has constant V, constant T, which is it's the temperature of the system and the temperature of the environment is the same, and no molecules can leave or escape the system. So delta S is the delta S of the system, and then delta S of the system and the delta S of the bath, when added together, should be greater than or equal to zero. How do I define delta S of the bath? I know it is, for example, in this case, there is heat flow into the system, right? So this is a thermal bath. Therefore, the temperature is not changing. So I can define entropy as Q reversible by T, okay? Because heat is flowing into the system, the entropy change of the bath is minus Q reversible divided by temperature. This is the entropy change of the bath. This is the entropy change of the system of interest. Both these things when added together, has to be greater than or equal to zero, right? So because this entire system is an isolated system. This analysis we have seen in the previous lectures. This is a statement of second law, the entropy change of an isolated system. I'm going to just rearrange this formula in the following manner. I'm going to multiply this as T delta S minus delta U. When I rearrange this, I have this term. And then if I multiply by -1 on either side, I have del U minus T del S is less than or equal to 0. With another simple change, what is the change I'm looking at? I'm introducing a new variable, new thermodynamic function. Again, this is the Helmholtz free energy that we defined in the previous lecture as U minus Ts. When I introduce this variable, what is the advantage? You will see that. Del A is del U minus T delta S plus this term, right? But this is a system for which T is kept a constant because it is in constant thermal contact with the environment. So delta T is not changing. Therefore, even though I mathematically can write this, delta T is 0. Therefore, this term is equal to del A. So I can introduce a new term, new thermodynamic function, Helmholtz free energy, where at equilibrium, del A is equal to 0, or for a system wherein, like from the previous slide, a system for which V is kept a constant, T is kept a constant, N is kept a constant, I have delta A is less than equal to 0. So notice all these are properties of the system. Okay, delta U is the change in internal energy of the system. Delta S is the change in entropy of the system. There can be reactions, chemical reactions that are occurring and so on. It doesn't matter. All these things refer to variation inside the system. Therefore, I can use a state quantity because all these things are state quantity, right? So if you look at this, this is state quantity, temperature is fixed for the system. This is a state quantity. Therefore, this is also a state quantity. For this particular experimental condition, del A is less than or equal to 0. In the homework problem, you will derive this condition, del G is less than or equal to 0 for a system where T, P, and N are 0. Okay. So between the previous slide and this slide, what have we accomplished? We have accomplished that there are, corresponding to different ways of doing an experiment, there are different thermodynamic functions, thermodynamic state functions, thermodynamic potentials that are natural to the system. In what way they are natural to the system? At equilibrium, they take an extremal value. Okay, so that is the central reason why we are using 5 different thermodynamic state functions to describe the different ways of doing an experiment. In the next lecture, we will talk about Maxwell relations and Clapeyron equation. Again, these are the practical utility of thermodynamics. Okay, so we are trying to relate thermodynamics to material properties. Okay, so as I said, when we introduced thermodynamics in the early part of the class, okay, so there are 2 major approaches in addressing thermodynamics. One is related to energy conversion, storage, power generation, and so on. The other is property, documenting the property of materials. Okay, so how do you make a measurement? Which measurements are easier to make? And when you make a particular measurement, what is the relevant thermodynamic state function? So that's what we are dealing with in this lecture and the next 2 lectures. Thank you.